we are discussing about this principal component analysis and its computation. Today, I will illustrate this computation using an example. You consider that you have this many number of points as your data set. So it's a three-dimensional input space, and you can see that all the data points they are a point. They can be considered as a point in a three-dimensional space. So, so your objective, or rather, you are asked to do the principal component analysis, and you can find out whether it is possible to reduce the dimension. As you know that we are trying to retain the variances of the data as much as possible, total variances of the data by reducing the dimension. Now, if you remember what we discussed in the last class, so we considered that input data points, they can be represented in the form of a data matrix. And how the data points are represented here in this matrix? So it is already shown here. So how a data point is represented? Anyone can tell?
Each column corresponds to a single data point.
Right. So every column, so you can see here that every column is a three-dimensional column, right? And they are the data points. So we have 5 data points, we have 5 columns. So which means the dimension of the matrix would be the dimension of the data point, which is 3 here, and cross the number of data points, which is 5 here. So now what are you going to do in this computation? You are going to compute the covariance matrix of these data points, which means can you tell me what are the steps, if you can remember the algorithms, what I need to compute first?
So we need to center the data points first, so
right,
we have to calculate the mean.
Very good. So that is what we did here. So this is the mean, actually mean of the columns. So you get again a column vector as the mean, and then centering means you are subtracting mean from each column, and this is a centered data point, and then you have to compute the covariance matrix. So what is the covariance matrix computation? What that computation means?
X bar by n, X bar by n, X transpose by n.
Can you be a bit more explicit?
Like,
X multiplied by
X squared, then X squared transpose, X squared transpose,
X square.
X transpose.
That's fine, but no. What is a covariance matrix? It is you can talk in terms of X tilde. That is the centered data point. So
X tilde X transpose.
yeah, and also you have to take the average. Okay. So this is the covariance matrix, and then what you need to do for finding out the principal components? For this
Eigenvectors and
eigenvectors.
You have to find out the eigenvalues and eigenvectors. So eigenvectors are the directions of principal components, and there you should rearrange the eigenvectors in such a way that the eigenvectors are, or rather you should arrange the eigenvectors in terms of decreasing eigenvalues, so that the first principal component, second principal component, those things comes. Of course, when you so this is your covariance matrix. As you can see here, this is a covariance matrix. Can you tell me that what these diagonal terms indicate?
The variances between
Variances
of each of the data points.
Yeah, dimension in each dimension of the data point. Okay. So, for example, this variance 1.04 comes from using these data points. The first dimension. I mean, there are 3 dimensions. Similarly, 41.6, this is contributing to that variances, and 42.24, this is contributing to that variances. Is it clear? Okay. So when you perform the eigenvector, when you if you find the eigenvalues, you know, eigenvalues are actually variances along the principal component directions. They are the principal components. Sorry, yeah, they are the variances of the principal components. Which means along those directions, if you take the projections of the data point and if you compute the variances, then that variances would be the corresponding eigenvalues. Did you get my point? Okay. So what should be the total variance of the data? What is the definition of the total variance of the data? So total variance of the data is the sum of these individual variances. Total variances of the data is sum of these individual variances. That is a kind of measure. Okay. So the property is that if you take the eigenvalues, so sum of these eigenvalues, since they are also variances along those principal directions and they are also those directions are also orthogonal, as you see here the axis is orthogonal axis and you are also transforming into another set of orthogonal axis. So the sum of total variances that remains the same. So which means sum of eigenvalues should be equal to, what does it mean? Sum of eigenvalues should be equal to what?
Total variance.
Pardon?
So that some of the eigenvalues will be equals to trace of this matrix.
Trace
so
of
that
this
will
matrix,
be the
yeah.
variance, some of the variances.
Right, that's right. Sum of the eigenvalues should be equal to the total variance, which is sum of the variances of individual dimensions along the individual dimensions. So these are certain interesting properties which you can prove easily, but no, just intuitively you can relate them, and that helps in various computations. So this is what I highlighted, these variances, and as you said that trace of this matrix can be considered as total variance, and that should be equal to the sum of the eigenvalues. So if we compute the eigenvalues and eigenvectors, so there is a numerical computation, you can refer to it, find out how they are computed. Then you get, these are the eigenvalues. You can say I have also arranged them in decreasing order. So the first principal component will have a value, it has the major share of total variance, 83.3238. The second principal component is 1.5562. And the third principal component that is interesting, that is 0. So my intention of showing you all these four till the fourth decimal place, because if you sum them, you will find that is coming exactly equal to the total variance. So you can see that one dimension is already redundant. Though you have worked with 3-dimensional data, actually this data can be represented in 2 dimension. So geometrically, what does it mean? Can you say that no, when this is a kind of structure, if you compute and if you find, somebody wants to say something? So tell me.
The data points can be represented on a plane.
Yeah, all the data points, they are lying on a plane. All the data points, they are lying on a plane. So I have intentionally taken this example in such a way that you can find out that they are all lying on a plane. So that is what I was trying to say. Now these are the eigenvectors. So these are the directions of principal components. So which means if I give you any feature vector x, right? If I give you any feature vector x, you should remember also there is an associated centered mean. Mean also you should remember of this transformation, right? So what should you do? You should first subtract mean from that feature vector x, then take all these projections, and then again you can add mean to it, right? So this is what you get this, and this is the uh, projection of the data points, central data points onto these axes, which means now you see that in this case, what you are getting actually, each row is representing your projected data points. It is not the column vector now. In my representation now, it has become each rows, isn't it? Do you agree? Okay, you have taken transpose of that, and then you can see every data point. So this component is the projection. I should use the pen. Say this component is the projection of the data point along this eigenvector. This component is the projection along this eigenvector, and this component is the projection along this eigenvector. So for you take any one, that is for the first data point which is subtracted from its mean of the data point, and then if you take the projections, then you get these are the values. This is the coordinate. So for every data point, you can see, of course, third component is 0, which shows that now this is the two-dimensional representation of the data point. So as you see, this dimension has become redundant. Actually, you can verify. It's a since I have just simply made this examples, so I can enforce this kind of thing. But in a real data set, you may get you will get some low variances in certain dimensions. It is not exactly 0, but now you can exclude them, ignore them. So you can have a new coordinate system, and if this is E1, E2, naturally E3 will be orthogonal to them, as you know. So that would be normal to this plane. That is what is E3. So E3 is given. So you can see the principal component analysis, as I mentioned, that it is considered also an analysis which determines the minimal subspace on which the data can be represented. So that is what I mentioned. So let us consider what are the interesting properties of principal component analysis, or PCA. One thing, as you can see, that it diagonalizes the data covariance matrix. So you will find out that your covariance of the transformed data. So it's a transformation. It's a transformation of one space to another space. As you can see, that it's a kind of rigid body transformation. From one set of orthogonal basis vectors, you are getting another set of orthogonal basis vectors. So you are making a transformation. And then in the transformed space, if you compute the covariance matrix, you will get only the diagonal elements, where each diagonal element will be one of these eigenvalues. So this is the representation, that your columns are unit eigenvectors of sigma, and you can show that this is the representation. So the components are uncorrelated in that sense. That means if you take the covariance between components, that would be 0. And by normalizing, so this also gives you a kind of normalization step, that when you have this kind of data spread, So you can normalize with respect to spread and bring them in a coordinate convention, so that say if you are comparing different points. So sometimes this Euclidean distance has a problem, that you have to use Mohalnevis distance and other things for comparing the distance when you have a covariance matrix. But when you have a diagonal covariance matrix, you can easily normalize it to use the Euclidean distance matrix. And also you have the reconstruction error from lower dimensions. So this is one of the properties that this projection gives you an optimum projection with respect to that number of dimensions. So whatever number of dimension you choose, say you want to project on only k directions. So it is in this principal component analysis will give you that set of directions where the residual error will be minimum. Residual error means the variances that you are excluding, that means the n minus k variances that you are excluding, which are when you are arranging them in the decreasing order. So that is one of the interesting mathematical properties. So some of the applications of PCA, if I quickly review them, one, as you understand that it is useful for data compression, particularly. One of the objective of data compression is that retain as much as information by reducing the requirement of data representation. And if you reduce the number of dimension, that itself will give you the compressions. But it is data dependent. That is one kind of I should say. That means, see, this principal component analysis, you are trying to capture the distribution. What is important is that when you are computing the covariance matrix and given a set of data points, you are trying to estimate the covariance matrix of that distribution. But still it is data dependent. So if you have another set of data points, so your transformation would change. So that is one kind of, you can say, feature. So if you can estimate the covariance matrix of the distribution very accurately or appropriately, then for a class of data in that particular class of data points, that representation is optimum. This is one of the name of this transformation, because it's a transformation, as I was telling you. So we call it also Karunen-Loeb transform. It is, you may also read it as a Karunen-Loeb transform, which is the same as performing principal component analysis. And you are getting an optimum set of basis vectors. Optimum in the sense, as I was telling you, that your reconstruction errors will be always minimum with certain number of, by choosing certain number of directions from that set. Now, one of the very popular transformations, orthogonal transformations, that is used in the signal processing and image processing domain, that is the discrete cosine transformations. In particularly, there are various discrete cosine transformations. One of the kind of discrete cosine transformations is called type 2 discrete cosine transform. You may not know all these details. I'm just giving you the technical terms. So it is not required that you should know all the details here. So the interesting thing is that it has been found to be an optimum representation for a large class of signals and images, because what we see that in these basis vectors, approximately the eigenvectors of a 2D matrix, as you can see with jk entries as r to the power j minus. So this is the covariance. The covariance matrix is element of the covariance matrix is modeled as from this kind of distributions, and it is approximately, it has been found that this is what the in practice in reality the the signals and images, they follow this kind of distributional, this kind of features are observed in their covariance matrices. So R is the measure of correlation between adjacent samples and a value near to 1. I mean, which is kind of intuitively, which supports also that adjacent adjacent samples should be highly correlated, and as you go away from a particular sample, naturally the correlation will fall. So with this kind of data arrangement, and that is what signal, image, that kind of data point has this particular property. If you consider any arbitrary vector, you do not have this property. But in signals and images, the adjacent samples, if you order them in such a way that adjacent samples, they have high correlations. So I'm talking of signals now, because in one dimension you are doing it, and then you can extend this analysis in multi dimensions. Along every dimension, you are considering the adjacent samples, they are highly correlated. Now, with these properties, which is quite, as you understand, which is quite realistic, that is how they occur. There is a high correlation among them. So, with that kind of objects, with that kind of, I should say, data, yes, the covariance matrix will have this kind of feature. I mean, the elements can be represented in this form. There are some applications of PCA. One I told about the data compression, and as you see that discrete cosine transform is heavily used for data compression because of this particular feature. The other thing is that as we understand that these principal components, they are decorrelated. So to reduce the redundancy in the representation, and rather it's a kind of factor analysis, though I should not say principal component analysis is I mean, it is not ideally a factor analysis in that sense, but it has certain indications of different factors which are there, because they are decorrelated. We are trying to decompose them into different factors. Only thing is that they are expressed in terms of your input observations of along every dimension. That is how they are expressed. The factor analysis has the reverse operation, which I am not going to discuss here. So one of the interesting applications of PCA can be found that that in the color representation, we have this color space, say red, green, blue, and any image which we capture through cameras, they have these three primary components. So the color mixing plays a very vital role in our perception, in modeling our visual perception of color. And that has a lot of implications in technology for color production and also the color acquisition, if I say, from the environment. Now, but they are very much highly correlated. One of the thing in the color representation is that there is a luminance part, which is roughly indicating the brightness, amount of intensity in the color itself, and the other one is the chrominance part, which is the colorness. And usually chrominance is represented in not usually chrominance is represented in two-dimensional space, but RGB, it does not have that kind of separation. I mean, everything like a color, red, green, blue, and together they represent the luminance representation. But if we can decorrelate, we can find the intensity part and other chrominance part. If you can perform PCA, that means you consider a class of color images and then compute the corresponding covariance matrix with respect to these three-dimensional vectors. All the color points you should consider, compute the covariance matrix. And then if you perform the principal component analysis, you will get eigenvectors. And one such analysis, I mean, this is a paper at the bottom, right bottom, I have just refer to that paper. Somehow the year is missing, but it is quite old paper in 80s, maybe 83, 84. So in this paper, it has been shown that with experimentation that these are the components they can find out, and it has certain also some interpretations with respect to the color representation. Moreover, it is I have mentioned with respect to color images, but if you consider remote sensing images, there are so many bands of images that you know. There are multispectral images, hyperspectral, ultraspectral, and there are tens, hundreds, thousands of bands. So I hope you understand what is a band here. Band is a particular spectral wavelengths, the range of wavelengths along which your sensors are sensitive to those wavelengths. So these are all passive sensing. I'm talking about passive sensing here. So as you know, in the camera also, your sensors, these optical sensors, that is sensitive to the optical range. That means optical wavelengths. Similarly, there are microwave, in general, there are different microwave bands. And in that band, so there are certain sensors which are active, which are sensitive. So using this kind of physical properties and physical properties of the sensors, you can design the cameras, and you can sense the environment into different bands. That means images into different bands, and it could be a large number of bands. Now, to process this information, once again, given a particular scene, it may be that only a few bands or a combination of these bands, they are sufficient to represent the information. You do not require thousands of bands, maybe a certain combination. So how do you get them? There you should perform this kind of principal component analysis to find out the data. So one example has been just highlighted here, that it is a kind of hyperspectral images, and maybe 100 bands are there. But I'm just showing here from this paper, of course, I've taken this figure from a paper. So they are showing the 20 principal components, which are, as you can see, from the topmost and leftmost image, that is the first principal component. It contains a lot of information. And if you look at the bottommost and rightmost image, let me use the pen. So I'm referring this image, and this is the first principal component. If you can see this number, it's a bit, and this is the 20th principal component. So in this order, the principal components are arranged. So this is this order, in this order, left to right, top to bottom, in this order. So as you go in this order, then you can see that information content is reducing. By looking at the picture visually also you can understand. And so it is sufficient if you just compute with these 20 components only for any purpose. Say you are trying to classify certain objects, doing some land cover analysis. So it is not required that you should do with all 100 components. So it saves your space, it saves your time. So this is one kind of applications. So it removes the redundancy. Factor analysis I just mentioned. So let me just briefly highlight one thing. By looking at the these components, and if you consider the corresponding eigen directions, eigen vectors, so each vector is like giving a factor. That means this is a combination of all these vectors that is giving the data point. Okay, so you look at from that angle, though these vectors are also from those data points. So they are not independent in that sense, but still, no, they are representing something. So one of the interesting part is that there is a technique face recognition technique using this kind of eigen face recognition. So what it does essentially, it does principal component. So you take a collection of faces. You take a collection of faces, and then you find out the principal components, and these are the first few principal components which are which have sufficient strength variances. And then you can see that on the roughly they are capturing different zones of the face information. So given a face, I'm sorry, given a face, what you are computing along this for all these components, what is the coefficient? So the linear combination of these components will give you a face. So those coefficients represent a face. Now use it for classification. So this is one kind of application. So in the classification or high-level processing, this type of representation using factor analysis, one can do it. And in a briefly, we can summarize that how it is placed. So you have the original data points. In this case, I have shown in the form of images. Say this is that set of images or band of images. Then this PCA principal component basis vectors means those eigenvectors. And you have also fixed that how many eigenvectors you should choose, because you know that in your data distribution, how many principal components are retaining most of the information. So you perform the projections along those directions, and you get a new representation, a derived representation we call them principal components representation. So that is the dimensional reduction that takes place. And now this is your feature representation. So whatever classification you have learned earlier also is all those techniques that you can apply on this particular reduced dimensional space. So this is the implications. I think this is what you can relate principal component, how it is related with your this machine learning thing. So it is one way of feature engineering, one tool of feature engineering which is heavily used. Now I will consider another particular type of analysis, and which is quite similar to principal component analysis. That means which also uses the projection of data points along a direction. But in this case, the interesting thing is that it also takes care of the information of class levels. So in this case, it's a kind of supervised data on which you are trying to find out a direction, and your objective is not to preserve the variances, not to preserve the variances of the data in the projected points. Rather, your objective is that you are trying to get that direction on which, if you project those points based on your class levels, so that they should be well separated. That means data points of different classes should be projected with maintaining a separability. They should be distinguishable. Is it clear? Is there any query? But that is what is my comment here, that here, since my objective is different, my objective is not to preserve the information content, rather to get the separability, get the separation more prominent in the projected in the projected space. So the principal component analysis is not very much, I should say, it is not really addressing that issue, I should say. Where principal components analysis, it captures the direction of maximum variance for a data set. And in this case, we are trying to get the separations, maximum separations, which is not really captured in that direction, which may not, which may not. Say you take this example, it's quite self-evident. Say you have this two-dimensional space and you have these points, two-dimensional points, and by those corresponding markers, I have shown their classes. Now you consider a direction, as you can see here, that this particular direction, and if you project these points along this direction, so you know the rule of projection. Rule of projection is simply along that directions from a data point, you get the perpendicular drop, and the point of intersections with the perpendicular drop, that is the projected point. Okay, that is what effectively you have done that corresponding dot product of two vectors. It is trying to find out that point, and with respect to any one reference point, that is the origin of the point, you are getting the coordinate. Coordinate is length of the drop. I hope you understand that actually you are doing this kind of geometrically projection means this. So you can see that all these data points, they are mixed, right? They are not well separated, they are overlapping. But if I consider for this if I consider another directions for the same set of data points, say this is the direction now. Now you can say that there is a good separation between the projected points. So linear discriminant analysis tries to find out the direction of maximum separability. Any question? Okay, and this direction is called Fisher linear discriminant direction. So we will now rather discuss that how to compute this particular direction. So we have seen how we can compute the direction of the principal component. That we have seen, that using that covariance matrix, finding out the eigenvector and maximum eigenvector corresponding to the eigenvalue, you get the first principal component, and in fact you can get the all principal components by finding out the eigenvectors. But in this case, our problem, we are restricting our problem for this kind of two-class data distribution, and we are going to compute only one direction, and that is the direction along which the projected points should have maximum separation. So it's a heavy reduction of dimension in that sense. It will perform the classification, and no, for the purpose of classification, it is more effective, as we can see. If you can really get such a direction where they are well separated, then your task of classification becomes much simpler. Okay, but you may not always get. That is fine. But let us try to achieve at least a direction where it should try to achieve maximum separation. So let us consider this kind of framework, that you have a set of data points in the d-dimensional space, and suppose in this set, as I mentioned, there are two classes, and class W1, it has n1 points, and class W2 has n2 points, right? And your total number of points should be n1 plus n2. That means each point in the set S has one of these classes. I mean, they belong to one of these classes, right? So as I mentioned, the total number of data points should be n. So now we try to define an objective function with respect to a direction which will capture this separability property, so that if I maximize or minimize certain, if I can attribute with respect to that properties, and so the maximization or minimization, we'll see what we are trying to do. Actually, maximization of separation, that is our objective here. So we are trying to get some objective function so that the separation gets maximized. Right. So this is the projection of data xi on this direction u. Is it clear? Any doubt? I mentioned that no, in this case only one, we are representing all the data points after projection in a one-dimensional subspace, which means they are projected on a line. Now suppose the mean of the data point M1, that is the distribution of data points for the class W1, and for the class W2 this mean is M2. So what should be the projection of mean? So if I project the data point, so how the mean would be projected also? Mean point would be projected also M1 transpose U. Do you agree? If I get the mean of the data points, if I project it, what should be the mean? M1 transpose U. But what is the property with respect to the mean of the projected points? Can you guess? You can prove it very easily. What should be the property? The projected mean is the same as mean of projection. What does it mean mathematically? How do you express it? Because it's a linear operation, na? Projection, after projection, say this is what you get my1, my2. Actually, projection of means they are the same as the projected mean. So let me explain. Though you can prove, I have not proved here. I just gave a statement. So this is the projected mean, right? This is mean. M1 transpose U is the projected mean. So this is the projected mean, and my1 is the mean of the projection. So I have not mentioned, I have not defined it, but please consider that it is a projection. So mean of the projection. So all the data points which are projected of class W1, if you take the mean of the projections, that is M1. So they are same. So that is true for the other case also. So what is the measure of separation in this case? Through this figure, how do you can guess what should be the measure of separation of these two classes? So one measure of separation could be simply the distance between these two mean, right? But there is one limitation. Can you tell me what is that limitation? Will it really measure the, yeah, is it sufficient?
It will be single dimensional, single directional.
That is already there. We have accepted that fact. But is this measure
We also
sufficiently
need to
capturing?
find the standard deviation of that.
Yeah, you should also consider the corresponding spread. Na? See, mean is just does not represent the distributions. Even that the spread is also important. So in this direction, you might get projected means are well separated. But no, it may be that no, if you consider the spread of the projected points, or as you have rightly said, the standard deviation is measure of that dispersion, data dispersion of the projected point. So they should be also they should be small. If they are large, then no, there is a risk of getting more overlapping. Right? There is a risk of overlapping of these intervals. So that is why. So we should try to maximize this separation. So which is can be represented as the absolute difference between these two values, right? Length between these two. So simply absolute difference with this. These are two scalar values. You understand? These are two scalar values, right? So D should be maximum, and then we need to consider the standard deviation or variances of the data. So there is a term called scatter of data that belongs to a particular class C. Now this scatter is is nothing but it is actually a measure of variance. Only thing is that it's a term used with respect to this Fisher's linear discriminant analysis because no, it has some advantage over mathematical notations later on. So we are not averaging, we are simply happy with the sum of square of deviations, and that is what is scatter. Square of deviations from the mean, right? Okay. So you have scatter of class 1 and scatter of class 2. And if you add them, that is the total scatter, right? So measure of separation, finally, this is the objective function. That is what we are trying to maximize. We are normalizing the separation by this total scatter. Rather, I should say square of separation by this total scatter. And we would like to maximize it. So we'd like to maximize this particular objective functions to get the direction A. Okay. So why actually we consider scatter instead of variance? Because of just from mathematical convenience. But if I would have said they are variances, you were almost right, except the fact they are not variances. I mean, as you understand that they should be multiplied by the number of samples. Then variances should be multiplied by the number of samples. Then it becomes scatter. So so one of the thing is that we have considered scatter of the projected points, because variances are well defined with the scalar values, scatter of the projected points. But what happened when we consider the corresponding classes? So there is a relation between the earlier also you have seen that there is a relation between covariance matrix and the variances in the projected direction. Can you tell me what is that relationship? That we have already discussed. Suppose you have a data point, say I'm representing this as a distribution, and it has a covariance matrix sigma. And then you have a direction, say U, right? And which means you are a direction of projection, and you are taking all these projected points on this direction. Is it clear? So now you compute the variances of this particular, I should write sigma square. You compute variances of, say, sigma square, variances of these projected data points, projected values. If I say projected values, that would be more convenient to understand. Point is always associated with always a coordinate, but actually we are considering here, say, values when we are considering. So basically value of the coordinate, right? So what is the relationship between the covariance matrix and this, between covariance matrix, this direction, and this sigma square? What is the relationship? Can you, if I give you covariance matrix and if I give you a direction U, and if it is an orthogonal projections like this, so I can compute sigma square. I need not compute the projection and get sigma square. Can you tell me?
So the eigenvalues of the covariance matrix.
Eigenvalues of the covariance matrix. You see, what are those eigenvalues of covariance matrix? Their eigenvalues are variances along certain directions, but that is not the variance along U. They are the variance along, I should say, principal directions. Eigenvalues of covariance matrix
sigma U transpose.
You are telling something. You tell me once again.
U sigma U transpose.
U sigma U transpose or U transpose U sigma? Sorry, U transpose sigma U.
Yes, U transpose.
You check the dimensionality, that is better. See, variance is a scalar value, and we have considered this is column vector. Okay. It is important to understand your convention. So if it is a column vector, so what is the dimension of U? Say dimension of data is D. That is a D-dimensional space. So dimension of U should be D cross 1. Clear? What is the dimension of sigma? What should be dimension of sigma?
D cross D.
Yes. D cross D. And what is the dimension of U transpose? It should be
1 cross D.
1
1
cross D.
plus 2.
Right. So if you do the multiplication, matrix multiplication, I mean with the dimensional check, then it becomes 1 cross 1. Just looking at the dimensional check, no, sometimes you can say whether your expression is correct or not. I mean, if you have confusion, please always go by this dimensional check. And it always is tied up with the convention by which you are representing your vectors, etc. Matrices, your data, whether it's a column or whether it's a row, that is very important in your convention. So today, let me stop here.